Here we are, homework number 9. Homework number 9. This will be due on Wednesday. So prime factorization. Let's take the number. So question number 1 is find the prime factorization. Prime factor the number 300. So can we do that? Can you take? So basically, we want to take 300 and break it down to all those little numbers that make it up. That's what today, really this week and next week are all going to be about. It's all about primes. The fact that primes make all the other numbers. I think I talked about it last time, didn't I? Said it's like the periodic chart, the elements that make everything, or the letters in the 26 letters in the alphabet that make all the words. That's kind of like what primes are. Those are the numbers that make all the other numbers. So the primes are really the most important numbers because all the other numbers are just made out of them. So here we go. Let's take the 300. I'm sure you've done this before. Let's just break it down and say, hey, what times what is 300? What multiplies to be 300? There's a lot of things. You could say 2 times 150. You could say 3 times 100, 30 times 10. It doesn't matter. Start however you want. I'm probably just going to go 3 times 100. But anything is fine. It'll all end up the same in the end. So 3 times 100. And now the 3 is done, isn't it? You can't break down 3 anymore. He's a prime, right? I mean, you could write 1 times 3, but you're using the 3 again, so you didn't really make it smaller, right? So 100, what times what's 100? Again, lots of things. You could go 4 times 25. I'm just going to do 10 times 10. I think that's about as easy as anything. But again, it doesn't matter. It'll all end up the same if you keep breaking it down. And then what times what's 10? Just 2 and 5, right? And those are primes, so we're done. Okay, so what's the breakdown then altogether for the 300? 300 is, notice, 2 2s. So I'm going to put them in on numeric order. You don't have to, but any order is fine, really, but it's just easiest to look at, I think, that way. A single 3 and 2 5s. So 2 2s, a 3, and 2 5s. 2 squared times 3 times 5 squared. That's the breakdown of a 300. That's the guts of a 300. Those are the little prime pieces that make the number 300. Notice if you took your calculator, and you want to have a calculator next week for the exam. You can't use your cell phone, of course, right? Because you could call out for answers in the middle of that. And not that you would, but I have to keep it secure in case somebody would. So you can't use cell phones, so make sure you have a calculator you're comfortable with for the exam next Friday. Anyway, so yeah, if you just did 2 times 2 times 3 times 5 times 5, you just multiply those together, 300. You'll get 300. So we just found the breakdown of a 300. That's called the prime factorization. Those are the primes that make up a 300. 300 is made out of 2 2s, a 3, and 2 5s. They're the primes that make him. All right. Good. Let's try number 2 now. It's going to have a little more of a trick to it. There it is right there. I'm going to make it bigger. Let me see, 35 to the 4th. So number 2 says 35 to the 4th times 65 times 9 to the 15th times 65 times 9 to the 15th. And it says find the prime factorization. So same thing. Break down that number. Now, you might look at it and go, what do you mean break it? It's already broken down. Not quite, huh? Why is it not really? It's partially broken down. We mean all these together. That's all one number, just in his various pieces. But those pieces can be further broken down, can't they? See what I mean? Like 9, for example. 9 can be broken down to 3 times 3. And 65, 5 goes into 35, 5 times 7, right? So it's like, that one's like partway broken down. They want us to go all the way. Break it down the rest of the way. Now, it's kind of weird when there's powers on there. Let me make sure you're comfortable with that. So 35... and again, you can use your calculator and everything. If you're rusty on some of these times tables, no problem. Just use your calculator. So 35, 5 times 7, you might remember. Now, what about the 4th power? Well, that would just mean that the 35, the 5 times 7, the whole thing is to the 4th power, right? So there's that. And then 65, just use your calculator. 5 goes in. So just take 65, divide by 5 in your calculator, and you'll find 5 times 13. And then 9 is 3 times 3, and those together are to the 15th power because the 9 was to the 15th power. Good so far? It's making sense? Just kind of finished breaking down those numbers. And now, what do we do with the powers that are like on the parentheses and stuff? I think you know, don't you? I mean, I wouldn't try to think of some fancy algebra rule or anything. Just be real. You know what a fourth power means on anything. It just means 4 of those, doesn't it? So that just means 5 times 7, 5 times 7, 5 times 7, 5 times 7, doesn't it? It just means 4 of those. Now, I don't want to write that out. That's not the most convenient way. But so I'm going to do something else. In fact, how many 5s is that altogether? Just 4 of them, right? Just 1, 2, 3, 4. The order doesn't matter. You know the order of multiplication doesn't matter. You can shift it around, right? Like 2 times 3 and 3 times 2 is 6 either way you do it, right? So I can shift this all around. So I'll just make it 5 to the 4th times 7 to the 4th. And then I'll bring down the other things, this 5, this 13. And then what about the 3s? What about this 3 to the 15th power? Can I write that a little cleaner? That's 3 to what power? How many 3s altogether do we have there?
30.
There's 30 of them. Remember to see there's 30 of them? Because there's 2 of them repeated 15 times, huh? So there's just 33s altogether. Isn't that good? Now, isn't there like an algebra rule there where you can go 3 squared to the 15th like that? Yeah. And 2 times 15 is 30. Yeah, sure. If you remember all those rules, that's great. That's what we just did. I always think math is better to be done by just common sense. It's just 2 3s, 15 times, that's 33s. Yep, both are true. The rules are okay too. Anyway, we're almost done here. Can we combine any of these things together? And let's put them in order. The lowest one is that one, so I'll start with him, 3 to the 30th. I'm going to go in numerical order from the lowest prime to the biggest. So we'll start with 3 to the 30th. What comes next? How many 5s do we have? Yeah, 5 of them all together? We good there? 5 of them all together? And then 7 to the 4th, and then 13. And there we go. There's as much as you can break down that number. There's the final breakdown for that. Is that good on that? Questions on that one? I'll move on if you're good. Is 1663 prime? Is that a prime number? Maybe that's not the best number. That's a hard one, isn't it? Here, let me change it. I'm going to change the question. Is 899 prime? Is 899 prime? What do y'all think? By prime we mean does like anything else divide into it, right? You know what prime is, right? Can't be broken down. Does anything else go into it? I mean, other than 1. 1 goes into everything, we know, huh? And of course the number itself, 899, goes into itself. But does anything else? Do any other numbers go into 899? If nothing else goes into it, then it's prime, right? So what do you think? How can we answer that question? A question like this will be on your exam next Friday. How are you going to answer that question in a reasonable amount of time? What if we had like unlimited time? What if we had unlimited time? Could we answer that question? How would we do it? And we had a calculator. What would we do? If you're locked in a jail cell, they said you can get out. You're locked in some. And they say if you answer the question, is 899 prime? And you get one answer. You give the answer, and if you're right, you're out. If you're wrong, you're in for life. I'm sorry. I'm trying to make it serious. And you had to give the right answer. You got unlimited time. What would you do? How could you really find out for sure whether that number's prime or not? Would you really not know what to do? So what could I do with my calculator? My life depended on it. And I wanted to find out if 899 was prime. I wanted to find out if anything else divides in. Couldn't I just start going through the numbers? I mean, just start with 2. Does 2 go in? Does 3 go in? Does 4 go in? Does 5 go in? Does 6 go in? Does 7 go in? Does 8 go in? I just started out. I'll just take 899. I'll just take my calculator. Take 899 divided by 2, and I got 449.5, which is not clean, right? We mean goes in clean. No decimals or so that'd be a no. And you already knew without hitting the buttons that 899 did not divide by 2, right? How'd you know? How'd you know 2 didn't go in evenly? Because it ends with a 9, right? You know the rule for 2. But you all have a calculator on the test. I don't care about all those rules. As long as I just want you to be able to get the question. So then how about divide by 3? Does it work for 3? My calculator again says no. 299.6, blah, 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 blah. No. Divide by 4? No. I'll just say no. So so far none of these are going in clean. But there might be some other number up the line that does go in clean, right? How do we know? Well, we can go all the way to 899. Just keep dividing. That would take a long time. That's probably not what you want to do on the test Friday, a week from Friday. So you need a quicker method, right? We need a method where we can answer this question without spending, a whole hour dividing all the numbers. So this is a great example of what I anyway enjoy about math and science. I like a hard question like this that seems like, that's a hard question. You got to divide all the numbers up to 899. And with a couple, in fact, I'll make 2 nice observations, true observations, will take this hard problem and make it simple with 2 good pattern observations. And that's all math and science is looking at patterns and making a conclusion. That's all they are. And that's what you want to teach little ones about math and science. It's just getting better and better at watching patterns, predicting patterns, describing patterns. It's all about patterns. So first off, let's think about, did I really need to check 4? We're looking for 2 observations. The first observation. Why did I not? I bet you know, huh? Why did I not really need to check if it was divisible by 4 on my calculator? I already should have known the answer, huh? I bet all of you know. Why? Why don't you need to check 4? We'd already checked 2 and 3. We tried to see if 2 went in. We tried to see if 3 went in. 2 and 3 did not go in evenly. So could 4 have gone in evenly? How do we know for sure 4 could not have gone in evenly? Yeah.
Because 4 goes into 8 twice, and then after that, 4 doesn't go into 9. Because it's going to be 0 and then 9, 9, so 4 doesn't go into 9.
So, because 4, what's that?
4 doesn't go into 9.
4 doesn't go into 9. You're looking at those numbers. Yeah. So you're thinking out the long division. Yeah, I like what you're thinking. You're thinking, look, 4, I know 4 is going to go into 8. That part's going to work. But then you bring down the 9 or the 99. 4 is not going to go in evenly. Good. Very good. How about, I like that. That's an excellent observation. I'd rather do it even quicker, but that's a good observation. I like what you're saying. Is there another way where I don't even have to think about long division? But you're right. Thinking about long division, you can tell that's not going to work. You're right. How is it related to 2? Yeah, is 4 prime? No, what's 4 made out of? 2 times 2. We already checked 2. 2 doesn't go in. How could 4 go in? 4 is made out of 2 2s. That'd be like me coming up to this door over here and going, hey, we're trying to move, it's moving day. Moving days are painful, aren't they? So this door's open. I don't know where this door goes. Anyway, so if it's moving day and I want to move a refrigerator in there, really wide, double wide refrigerator. So, we come here, nope, it won't fit through the door. Okay, yeah, I understand 1 refrigerator won't fit through, but maybe 2 will fit. Well, that would be a silly question. If 1 refrigerator doesn't fit through this door, certainly 2 refrigerators are not going to fit through that door. Right? That's what we're doing here with the 899. If 2 does not go into 899, how could 2 2s? I don't even need to check 4. He's made out of 2 2s. He's a composite number. He's composed out of 2 2s. All right, let's keep going. Does 5 go in? You can use calculator. You can tell it doesn't end in a 5, right? You try calculator. No. Does 6 go in? Do you think 6 goes into 899? Think about 6 for a second. He's not a prime. What's he made out of? What's in a 6? What times what is 6? 2 times 3 or 3 times 2, either way you want to say it. And we've already checked 2 and we've already checked 3. and they don't go in. So how could 2 times 3 go in? No way. No way. I'm not even going to bother to check. Does 7 go in? I have no idea. I just used my calculator. No. Calculator said no. 8. Do I need to check 8? What's he made out of? 2 times 4? And that's 2 times 2 times 2 if you want to break it all the way down, huh? It's made out of a bunch of 2s. I already know. I was trying to put 3 refrigerators through the door. No way. No way. I don't need to check that. I already checked 2. How about 9? Do I need to check 9? Is 9 a prime? What's 9 made out of? 3 times 3. And I already checked 3. 3 doesn't go in. How could 9? So, are you seeing what numbers do we not need to bother checking? Or put the other way, what numbers do we need to check? Either way you want to say it. Do you see the pattern of what we need to check and what we don't need to check? Which numbers can we skip? We can skip numbers like 4, 6, 8, 9. You might say even numbers, but 9's not even. What kind of numbers are 4, 6, 8, and 9? Those numbers don't even need to check. Numbers that are made out of other stuff. Right? What do you call numbers made out of other stuff? Composites. They're composed. Not primes, in other words. So there's our first observation. Observation number 1. You only need to check the primes. Right? If you're trying to find out if anything divides evenly into 899, you only need to check the primes because all the other numbers are just made out of the primes, aren't they? So if you've checked the primes, you've checked all the numbers because all the other ones are just combinations of the primes. You see how the primes are the most important numbers? That's what this week and next week are really all about. You'll see that this is our first flex of power. How we can answer a hard question easily by thinking about primes. Because primes are really the building blocks. They're what make all the other numbers. So they're all you need to check. They're the important numbers. The other ones are just made out of primes. So all you need to check is the primes. You don't need to mess with any composites. So that eliminates more than half the numbers right away. That's a very helpful pattern observation. See, that's just looking at a pattern, isn't it? That's just looking, well, look, 9's just made out of other numbers. So if 3's don't go in, how could 9? We're just seeing the pattern. Okay, so there's our first observation. But that still leaves a lot of numbers, doesn't it? Like next would come 10. Do I need to check 10? No, he's made out of 2 and 5. I've already checked 2 and 5. Next comes 11. Does 11 go in? I have no idea. 11 kind of looks like it goes in. Let me try it. Nope. 11, no. So I did need to check 11, right? Because he's prime. You got to keep going. Do I need to check 12? No. In fact, I don't need to check any more even numbers, do I? Because they're all, 2 will go into them. 12, 14, 16, 18. 2 goes into all those. And so they're not prime. There's only one even prime number, and that's 2, huh? Let me say that again. This is the only even number that's prime. All the rest of the primes are odd. Right? Hey, by the way, 1 is not prime. I don't know. I'll write that somewhere. 1 is not prime. They basically just defined it that way. Sometimes people think 1, but anyway, 1 is not officially prime. Anyway, let's keep going. So 13. Does 13 go in? Try it on your calculator. No. Don't need 14. 15. Do I need to check 15? He's made out of 5 times 3. I'm not even going to bother to check him. He's a composed number. 16, 17. Let's try that one. Because 17 is certainly prime, and maybe it goes in. I don't know. No. Okay, this could go on for a while. Let's go a little further. Next would be 19. No. Next would be, I'm not even checking even. See, I'm skipping all the evens because none of them are prime. 21, do I need to check 21?
No.
7 times 3. It's composed out of 3 times 7. So, I mean, you can check it if you want to. It won't hurt anything. But I'm saying you don't need to waste your time. No way it could go, because 3 and 7 didn't go, right? 3 didn't go, 7 didn't go. So there's no way that 21 could go. But if you check it, it's okay. It's just a waste of time. Anyway, next comes 23. Does that go? No. All right. This could go on and on. We have to go all the way to 899. This could take a long. You don't want to do this. We need one more key observation to help us, so we don't have to go so far. Right? This is still going to take a long time to get all the way to almost 900 on your exam. You don't want to do this on your exam next Friday. Right? It's just be one question out of 25. You don't got time for this. So we need one more key pattern observation. Let me help you to see. This one's more complex. Let's think about what it means to be in a number and to multiply to be the number. Because that's what we're asking. We're saying, does anything times to be the 899? That's what we're really asking. Well, let's think about a nice, easy number that we know quite well, like 100. What times what is on? Let's start with 1. That's easy. 1 times 100. Then let's go to 2. 2 times 50, right, is 100. 3 doesn't work. How about 4? 4 times what's 100? Yeah, 4 quarters is $1, huh? Next, let's go to 5. 5 times what's 100? 20. 5 times 20 is 100. Next, 6 doesn't go. 7 doesn't go. 8 doesn't go. 9 doesn't go. 10 goes. 10 times what? 10 times 10 is 100. Notice the pattern. It's all about math and science. Like to say, careful observation. Notice the pattern. What's happening on these numbers as we go from here? They're getting bigger, aren't they? They're getting bigger as we go down this way. And what's happening to the numbers on this side? As we go down, they're getting smaller. And then right here, they come together. Right? So the numbers on the left side are getting, the numbers on the left side are getting bigger. The ones on the right are getting smaller until they tie. They started off way far away from each other, and now they've tied. And if we go beyond the tie point, the number on the left's going to get bigger than 10, and the number on the right's going to get smaller than 10. They're going to cross over each other, aren't they? What would be the next number after 10? Getting bigger. 1, 2, 4, 5, 10. What's the next number after 10 that goes into 100? 11 doesn't go. 12 doesn't go. 13 doesn't go. 20. It's all the way to 20. Big jump. 20 times what's 100? 20 times 5, right? See how this one got bigger, this one got smaller? Has to, because they're still making 100, aren't they? So this one got bigger, that one got smaller. Now the one on the left is bigger than the one on the right. See how the one on the left is much smaller than the one on the right? Then they get closer, tied. And now the ones on the left are bigger. And not only that, have we seen this before? It's right there. They're flipping. Yeah, next would be, what would be next? 25, yeah. Times 4, that's still got a little bigger, a little smaller. And then next would be, 50, all the way to 50 times 2. And then 100 times 1. Do you see that all of this is what? It's repeat, isn't it? After the crossing point, 25, it's up there. 20, 25, 40, it's all repeat stuff, isn't it? So the only new stuff or original stuff is in here. This diagram's getting really messy. This is the original, or this is the whole story, right? Once you get to this tie point, it's all just going to repeat after that, isn't it? So let me clean this up a little bit. So if you take 100 and you say, okay, I want to find out all the numbers that multiply to be 100, right? Then if you wanted to find out all the numbers that multiply to be 100, what you would do is you would just take your calculator, start with 1, 2, 4, 3 doesn't go, 4, 5, 6, 7, 8, 9 don't go, 10. And as soon as you get that tie, stop. You've got all the numbers. right? Because after that, it's going to repeat. See how this, 20 and 5 was a repeat of 5 and 20. 25 and 4 is a repeat of 4 and 25. They're just going to repeat because these numbers are going to get bigger and these numbers are going to get smaller, and that's just going to be reverses of the other numbers, isn't it? Okay, great. So what? Well, remember what we're interested in when we're looking at this 899 number here, we're trying to find out what might times to be 899. Because if you multiply to be 899, that means you go in there, right? So we want to find what numbers might go into an 899, might multiply to be 899. How far do we need to go? If you want to find all the numbers that go into 100, you only need to go till they tie. After that, it's going to repeat. You don't need to check those other ones. It's just going to repeat. Okay, well, what's that tie place? How do you find that tie? I keep saying they tie. 10 and 10. 100 is equal to 10 times 10. That's the tying place. Well, how could I have found that from the beginning? I could have said 100 is what times what? What number times itself, huh? And what would you say? Is that Abby? Is it divided by 2? 100 divided by 2 would be 50. Not quite. You're close. Something with a 2. What do we have to do with the 100? What do you got to do to 100 to get the answer 10, which is the tie place? See, if they were adding, it would be divided by 2. If we're saying what two numbers add to be 100, be 50 plus 50. What is it? I'm saying, yeah, what do we do to 100 to get the answer 10? 10 square rooted. Or 100 square rooted. Yeah. Right? Remember that? That's exactly what square root does. He says, what number times himself is this thing? That's exactly what square root does. And that's the twice. What number times itself twice is 100? 10 times 10. Do you see? That'll give you the number times itself that makes up. So if you want to check a big old number, say like 1600, and you're wondering, how far do I need to go? Well, you just take the 1600, you hit the square root button, I think it's 40. And it'll tell you only go to 40. Because 40 times 40 is your 1600. After that, you don't need to check. Do you see that observation? That's going to save us a ton of time. That'll really limit how far we need to go. Does that make sense what I'm saying there? So when you get to 10 times 10, you don't need to check anymore after that. It's all going to repeat. So if none of those have gone in, nothing could. They just repeat after that. And how do you find that tie point? You square root the number. You square root your original number, and you find out the last number you need to check. So there is a great observation and the pattern. So coming back here, number 2. Stop at the square root of the number. You don't need to check beyond that point. They're going to repeat after that. So if none of them have worked up to that point, nothing ever could. Because they're all just repeats after that. So I can stop at the square root of the number. Okay, so let's find, what's the square root of 899? Whoops, my date there. What is the square root of 899? Choose your calculator or your cell phone if you don't have one with you. I'm getting 29.98, blah, blah, blah. So 29, I can stop when I get to 29. Right? Stop. So if nothing goes in up to 29, then I can know nothing ever will. He's prime. So let's keep going. 23 said no. Do I need to check 25? No, he's 5 times 5. I don't need to bother. We've already checked 5. 5 didn't go. No way 25 could. Do I need to check 27? Do you recognize that number? What's 27? That's 9 times 3. Yeah, I don't know if you recognize it. It's okay if you check it. It won't hurt anything, but you don't really need to. He's made out of 9 times 3. We already checked 3 and 9 and don't need to check. So 29, yeah, we need to check 29. 899. This is the last one we need to check, right? If 29's a good, we're good. What's the answer? Some of you probably already know. 31. He goes. After all that, 899. Were you betting your life that he was prime? 899 is 29 times 31. He is not prime. He's composed out of two other numbers. He's just made out of a 29 and a 31. He's a Johnny-come-lately. He's not an original. He's made out of other prime numbers. He's a composite. So the answer is no, he's not prime. But that if that was the last one we needed to check, if 29 had been no, then I wouldn't have needed to check anything all the rest of the way to 899 because they're all repeats after that, after the square root of the number. See the power of that observation? So that one's a no-go. You want to try one of these? Let's try one.
Sure, why not?
How about if I give you, let's try, I don't know. Okay, we were going to do, well, it might be too big. How about 1217? Is it prime? And I have no idea. I just made this up off the. It sure looks prime to me, but I have no idea. It has a definite prime look to it, but so is the last number. So I don't know. So is that one prime? So try it out. So the two observations. You only need to check primes. So number one, only check primes. Don't bother with composites. They're just made out of primes anyway. Only check primes. Stop at the square root of 1217. Let's find that right now. You guys have your calculators? Find out what is the square root of 1217. Get that on your, it'll be some decimal thing. I'll get it also. It's 34.8, blah, blah, blah. So you can stop at the last prime up to before 34. You don't need to check beyond 34.8, blah, blah, blah. Okay, so how are we doing? Get an answer? Okay, so let me see. So I'm going to take it. So divide by 2 is a no. Divide by 3 is a no. I can tell that one. I don't need 4. 5, I can tell that's no. It doesn't end in 5 or 6. I can do all those just by looking at it. But starting at 7, I need the calculator. 1217 divided by 7 is a no. Don't need 9, right? 9's made out of 3 times 3. 11. No. 13. No. So I'm just looking for something that goes in. 15, don't need to check. 17. Oops. No. Divide by 19. 19's a no. 21, don't need to check. 23. No. Don't need to check 25, 27, 29. No. 31 is a no. Do I need to check 33? Is 33 prime? Or is 33 made out of something? Made out of 3 times 11. So you don't even need to check it. I mean, you can do it if you want to. It won't go because 3 didn't go and 11 didn't go. But if you want to, go ahead. 33. So really, I'm done. This thing's prime. And I can be confident. Does that make sense? Nothing goes in all the way up to 1217. I don't even need to check all the rest of the numbers. I can know with confidence because of the power of these two logical observations from the patterns. We just looked at the patterns. We said you only need to check the primes. The other ones are just made out of primes. And you can stop when you get to the square root because everything after that's a repeat. That was the pattern. So I can stop at 34. Now what they're going to ask you in the homework is they'll say, what's the last prime you need to check? So it's not 34. 34 is not prime. So when you do the square root thing, that tells you the stopping point, but you got to back up and find the last prime up to that point. So what's the last prime before 34? It's actually 31. Because 33 wasn't prime either. Remember, 33 was 3 times 11. So they're going to ask you that in the homework. They'll say, what's the last prime that you would need to check to find out if 1217 is prime? The answer would be 31. He's the last prime number. Because 33 is not prime, 34 is not prime, 32 is not prime. So 31 is the last prime you would need to check. And we did. We checked them all. The answer is no. Nothing goes in. That number's prime. We good? That's how you do that next Friday? All is well? All right. So on to 5 we go. Find the least natural number that is divisible by 3 different primes. So that's fancy talk for saying find the lowest number that is divisible by 3 different primes. So find the lowest number possible that 3 different primes go into. It's kind of a funny question, isn't it? What do they mean by that? Find a number that 3 primes go into? Find the lowest number that 3 primes go into? How about I give you, how'd you come up with that? 2 times 3 times 5, which is 30. 6 times 5, 30. Is 30 going to work? Do we know that 3 primes go into 30? Yes, for sure. It's a dramatic moment there in the question. Yes, for sure, because it's made out of 3 primes. Excellent observation. Does everybody see that? That's got to work, doesn't it? Because it's made out of those 3 primes. Right? It's made out of 2, 3, and 5. So for sure 2 goes in, for sure 3 goes in, for sure 5 goes in. They're in there, aren't they? And it's also got to be the smallest, doesn't it? Because it's made out of the 3 smallest primes. See what a difficult question that would have been before we were starting to think about primes. If I just said, hey, start your calculator, start going, find some number, and you'd be trying, 10, 8, 11, 12, trying all the numbers. But we just know right away, just 2, 3, 5, 30, boom. You just make it out of those 3 smallest primes. That's got to be the smallest number that 3 different primes go into. Excellent. Good observation. All right. Number 8, this is really the last one. 7 is not hard at all, and you'll be able to see it on the YouTube. But Mr. Arborita, all right, there we go. Mr. Arborita wants to plant fruit trees. So they're using, Arbor Tree Day. They're being tricky here. All right. Mr. Arborita wants to plant fruit trees in a rectangular array. Blah, 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 blah. All right, let's start with a nice, easy 28. So if Mr. Arborita wants to plant his fruit trees in a rectangular array, he's got 28. I'm just going to start with part B because that's easier. 28 trees. How could he do it? If he's got, so number 8, if he's got 28 trees, I'll do part B here, 28 trees, he could do a 4x7 array, couldn't he? Right? He could plant 4 trees in 7 rows. So I'm doing 4 trees, 4 trees, 4 trees. So there's all 28 trees. 3, 4, 5. Yeah, that's a 4x7 array, right? 20. Or he could do a 2x14 array, or he could do a 1x28. That'd be just a big long string, but we'll count that, In other words, I just want you to see, they're basically asking, what are all the numbers that multiply to be 28? They're just coming up with a tricky little word problem and a tricky little name like Arborita to basically, because they don't want to just say, hey, find all the numbers that multiply to be 28. But that's what they're saying. That's what it really says. Find all the numbers that multiply to be 28. So let's be clear. That's really what they're asking. Find all numbers that multiply to equal 28. So how do you do it? Let me give you the quick and easy way, because this also will definitely be on the exam next Friday. Just start with 1, use your calculator, and that one's easy, 1 times 28. All right, and then go up to 2, and just use your calculator, 2 times 14. And then go up to 3, but 3 doesn't work. You can try 20 divided by 3, doesn't work. And then next comes 4, 4 times 7. Try 5, doesn't work. 6 doesn't work. 7, and you're repeating. And we already talked about how once the number on the right is smaller, you're in repeat land, aren't you? No need to go any further. These are all the answers. How do they want you to answer the question? They just want you to list them with commas. So the answer to the question would be 1, comma 28, comma 2, comma 14, comma 4, comma 7. Any order, it doesn't matter what order. They just want them all listed with commas, any order. With our moments left, let's try one more of those. Let's do the hardest one. So let's go back to part A, which would be the 196. Right, 196, yeah, 196. So here's 8A, 196. Can you list all the numbers? You guys have your calculator? Start with 1. Go to 2. So take 196 and divide by 2 on your calculator. Let me know what it is. 98. And then go up to 3. Does 3 go? I don't think it does. Try 3, it doesn't work. Go to 4, and that'll be 49, I think. Then go to 5, and I think 5 doesn't work. 6, I think doesn't work either. Yeah, because 3 doesn't go. 7, it works. Yeah, 7 times 28. 8 doesn't work. 9 doesn't work. 10 doesn't work. 11 doesn't work. 12 doesn't work. 13 doesn't work. 14 works, though. 14 times 14. Right? Isn't it 14 times 14? And once I get to there, anything after that's going to be repeat land, isn't it? Once the numbers go. So this, and this. So what are all the numbers that divide into 196? 1, 196, 2, 98, 4, 49, 7, 28, 14. Now you don't need to list 14 twice. Just list it once. So that would be the answer. Any order with all commas around them. There we go.